All right, everybody, let me clear this. Get out of here. Got to clear this before I started, all right? All right, one more thing to clear. Sorry about this, 1 second. Okay. All right, so we are on lecture 9, beginning of lecture 9. So we have lecture 9. This is part 1. And we're going to be covering chapter 6.1. Okay, we're now on to series solutions. Okay, let me tell you a little bit about what's going on and why we need this. So remember that we always are thinking about our equation that looks something like this, some function of x times the nth derivative of y plus another function of x times the nth minus 1th derivative of y plus dot 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 plus the another function of x times the first derivative of y plus yet another function of x times y equals some, g of x, right? This is kind of our general model for a linear differential equation. So we've learned about solving in the case where we've solved when the ANs are constants, right? And we even solved the inhomogeneous equation even for any function, g of x. And we've solved Cauchy-Euler equations that have that special form where the AN of x are equal to x to the n, right? So if this was a third derivative, this would be x cubed times that. Then we can actually solve that, right? This is x to the n. Okay. And then once we have solutions to the homogeneous equation, we can always, find using variation of parameters, etc., or undetermined coefficients, we can find our particular solution. So we know how to do this. But that's in these two cases, right? Where the ANs are constant or where the ANs have this form x to the n. That's that Cauchy-Euler equation. But what about some general, these AN of x have some general functional form that is not x to the n? And that occurs very frequently, of course. And the only way to solve those is with a series solution. And that's what we're going to start looking at today. So to start, though, chapter 6.1 is all about refamiliarizing yourself with a power series and what is a power series, etc. And how do you figure out if it converges? How do you multiply two series together? How do you add two series together? And all these little sort of mechanical things that you need to do for a power series, for series solutions. Okay, well, let's just recall what a power series is. So we have a power series. Looks something like this. We have a sum from n equals 0 to infinity, let's say, right? To be general. Some coefficients times x minus a to the n. That is a power series. And of course, if you expanded that out, right, so start doing the sum, you'd get, c0 x minus a to the 0, which is just 1, plus c1 x minus a plus c2 x minus a squared plus dot dot dot. And we call a the center. So we call the number a the center of the series. Now you must have had stuff like this in calculus. I might be just reminding you of stuff, etc. So if I had, something like this, sum over n equals 0 to infinity of cn x plus 1, then that has a center at a equals minus 1. That center is a equals minus 1. Okay. Now, most of the time, we'll be dealing with the case where a equals 0. Okay, so that looks like this: sum from n equals 0 to infinity. Sometimes I'll write this, the limits here, and sometimes I'll write them under the sum sign. It doesn't matter really. Where you have Cn x to the n. So that's an a equals 0 series, power series, and we'll deal with that probably more than we will deal with anything that has a center. Okay, and we call that a power series in x, right? Okay, it's because that's not centered at any other point but 0. Okay, so let's look back at some important facts, and I'm going to actually bring up the actual text. So let's remind you of some of the things that you may have once known from calculus. Convergence is something we have to worry about with power series. Does it diverge? Does it converge? And this idea of convergence is usually couched in this in terms of the partial sums. And a partial sum just means that you just sum up to a particular n, right? So a partial sum of this guy might be from n equals 0 to 5, right? And that would be big N in that case. And so what you do is you think about all the partial sums, so summing up to 5, summing from n equals 0 to n equals 6, right? And all those partial sums, as big N goes to infinity, if this limit exists, then this is convergent. Now, that's not the most useful definition for convergence that you can have, and I'm going to show you or remind you of the ratio test that we often use to test convergence. Anyway, so don't worry about this sort of formal definition. But the interval of convergence is important, and it tells you the interval in which it's all values of x for which the series converges, right? So the center of this interval of convergence is the center A, right? So here it's all values of x for which this series converges, right? And the center of that will be A, right? And it's often couched in terms of the radius of convergence. And if you have a power series and it converges for absolute value of x minus a less than r, and diverges past that radius, right? So we look at this little diagram here, you can see here's the center, here's a plus r, here's a minus r. The series diverges this on this side, so greater than a plus r, and diverges for a minus r. It's equivalent to saying this, that's what this is showing you, right? That a minus r less than x less than a plus r is the place where it's going to converge, okay? Now, a power series can actually converge inside and diverge on these endpoints here. Okay, we're going to see an example of that. It can diverge on both of them, it can diverge on one of them, or none of them. Okay. And don't worry about this absolute convergence. Okay, so let's move on to the next thing where we look at something called a ratio test. And if you remember what a ratio test is, it's a test for convergence. Okay, well, what do we do? So given a series, right, that you have like this, the series that's defined right here, right, what do? Well, you take the limit as n goes to infinity of a ratio of two terms, okay, and it's the absolute value of the ratio. So we have the nth plus 1 term, and then we have x minus a times to the n plus 1. So it's that n plus 1th term in the series over the nth term. So Cn x minus a to the n, and that's all absolute value. And we look at that and we decide whether it converges or not. So this we can rewrite. Actually, it's a little nicer. We have absolute value of x minus a. Right, because look at this. It's going to cancel one of the n's, and you're just going to have x minus a. So we'll pull the absolute value out because it doesn't have any n in it, right? And then we have the limit as that n goes to infinity of the absolute value of Cn plus 1 over Cn. And if that we call that L, right? If L is less than 1, then the series converges. Okay, and if L is greater than 1, it diverges. What if it's equal to 1? Well, if L is equal to 1, then it's indeterminate, right? It can't say anything. Inconclusive. Inconclusive test. Inconclusive. Okay. All right, so that's the ratio test. Okay. All right, well, let's see an example of this. Okay, so let me get a new layer because this is a messy mess. Okay. All right. Let's look at an example. So we have the series sum of n equal 1 to infinity. Notice it's not n equals 0. X minus 3 to the n over 2 to the n times n. So there's a reason it's not to start as n equals 0. We want to know does it converge and what is its radius of convergence. Let's look at our ratio test. So we're going to take the nth plus 1th term, and I'm going to bring that x minus 3 outside, the absolute value of x minus 3, because I know that's going to show up there. And now I'm going to take the limit as n goes to infinity of the absolute value of the nth plus 1 term. So that's going to be 1 over 2 to the n plus 1, and then n plus 1. And then over the nth term, which is 1 over 2 to the n times n, and I'm going to extend this down here. There we go. And now I'm going to simplify this. So we get x minus 3, and then we get the limit as n goes to infinity of this ratio. So let's simplify. So I have, so this is going to give me a 2 to the n plus 1 on the bottom, and n plus 1 on the bottom as well. And it's going to give me 2 to the n and then an n. And I'm going to simplify some more. I'm going to move this guy out of the way a little bit. Oh, come on. Hold on a second. Okay, so, and one more simplification, I think. So we have x, absolute value of x minus 3, and then the limit n goes to infinity, and then this 2 to the n cancels this 2 to the n. I just get a 1 over 2 on the bottom there. Of course, I could just bring out, but anyway, I'm just going to leave it there for a second. Then I have n over n plus 1. And I think you can see, remember what you do if you're looking at, what does the limit equal? You divide everything by the highest power that you have in here, and the highest power we have in n is just the first power, right? So n to the 1. And so I'm going to divide this by n, and I just get 1. Divide this by n, I just get a 1. And I divide this by n, I get 1 over n. And the limit as 1 over n goes, as n goes to infinity of 1 over n is just 0, right? So I get 1, all this is 1 in that limit. So I get x minus 3 absolute value, and it's 1/2 times 1/2, right? And we can see that this is less than 1 for certain values of x, right? Okay, so I want it to be less than 1, so I'm going to come over here. So I want x, and now I'm going to figure out what my radius of convergence is and everything, right? So I have 1/2 absolute value of x minus 3. It's got to be less than 1 for it to converge. So where is that going to happen? Well, I can solve for this, right? And think about this as this is the, well, here, let me write it one more time. X minus 3 less than 2, right? Because I brought the 2 up here. Okay, well, this is just like our other statement, and we can rewrite this as 1 less than x less than 5, right? Because that makes this true. Got it? So x has to be greater than 1, right? So if x is 2 here, what do we get? We get absolute value of minus 2, which is 2, right? but it can't be exactly 1 because it's greater, it's x greater than 1, not greater than equal to. Okay, and then think about x at 5, right? Again, the same thing, you get 2, but it can't be exactly 5. So this is our interval of convergence here, right? Outside of this interval, it does not converge, because then you would not have, this would not be less than 1, right? And you would have divergence. Okay. Now let's look at the endpoints. So this tells me that the interval of convergence is between 1 and 5, but there are two endpoints, x equal 1 and x equal 5. So x equal 1 and x equal 5. Okay, so if we put that into the series, so let's look at the series. So we have the series n equal 1 to infinity, and then of course it's x minus 3 to the n over 2 to the n times n. So if I put x equal 1, so let's start with that one. So at x equal 1, we have sum n equal 1 to infinity, and then we have x equal 1, which gives me a minus 2, right, on the top. So we have minus 2 to the n over 2 to the n times n. Did I do that right? Yeah, 1 minus 2. Yeah, okay. So I can just pull out that 2. It's just I just like to pull it out because 1 and then infinity. Because we have here an alternating series, right? So I pulled out the 2. Let's see. I have to be careful about that. So when I pull out the 2, I've got to cancel the other one. And I didn't do that. So hold on, let me fix that. All right, so bad. Let's not pull out the 2. I can pull out the 2, but I gotta keep it in the sum. Okay, so if I pull out the 2 here, right, then I have to, it's 2 to the n that I'm pulling out, obviously. Sorry about that, that was dumb. And that cancels that. And I ended up with this nice alternating series. Now there's a special test for convergence for alternating series. So let's bring that up. So if you look over here, there's something called the alternating series test. And if we have a series, say, where an is minus 1 to the n, bn, right? So in our case, what do we have? This is minus 1 to the n, yes. This 1 over n must be the bn, right? Right? 1 over n is the bn. And bn is greater than or equal to 0 for all n, yes. Then we can test for convergence by doing these two little tests here. Okay, so first we take the limit as n goes to infinity of the bn. The bn for us is just 1 over n. So you get the limit as n goes to infinity of just 1 over n, and of course that is 0. So good, this is a check on that one. And then the bn has to be a decreasing series, okay? So a decreasing sequence, well, I think you know it is, right? So 1 over n, so we have, 1 over 1, 1 over 2, 1 over 3, etc. That sequence is decreasing. So our second thing is a check, okay? So this is going to converge at this point. So actually I can put this here, right? Because this was 1, so at 1 it absolutely converges. What about 5? Okay, well let's stick 5 in. So we have sum n equal 1 to infinity, and then we have x, so x is 5, minus 3 is 2. So 2 to the n over 2 to the n, and that just gives me sum n equal 1 to infinity of 1 over n. Now you might think when you look at this, it's so similar to this, right? Except for it's not alternating. Okay. And you might also think, well, n is just going to get bigger and bigger, and that's going to make this smaller and smaller. Doesn't that converge? Well, in fact, it doesn't. Okay, this is one of those really famous series. So this is called a harmonic series, right? You might have heard that before. And it is divergent. There's some great videos of the proof for this. So it certainly isn't obvious that it wouldn't converge, but it is divergent. So that means that this less than sign has got to hold. It does not converge at x equal 5. Not good. Okay, so you can see how different values of x can change the convergence, right? That's the point. Okay, now let's write down a couple properties, and I'm going to just go down here and do it, or over here. We have what's called the identity property. Okay, the identity property says that if you have a sum, a series, right? Series from n equals 0 here to infinity, let's say, and then and it's just x minus a to the n. If that whole series adds up to 0, that means that and you know, there's other caveats, but I'm not going to add them in. That means that all the CNs are 0, right? Cn equals 0 for all. This upside down a means for all n. Okay. Now that hopefully is relatively obvious because these are powers of x, right? I mean x minus a, but still powers of x. And because the different powers of x are linearly independent, you have to have all the CN 0 if the whole thing is equal to 0, because they're linearly independent and they're not going to cancel each other out in any other way, right? So that's the identity property. It's useful. And we say, there's another thing, analytic at a point. And we say that a function is analytic at a point A if it can be represented by a power series, by a power series in x minus a, okay, with either positive or infinite radius of curvature. So it's got to converge on somewhere, right? So it can't be, it doesn't converge anywhere. Okay, that would not be good. So it has to converge either in some interval, some positive radius of curvature, right? Radius of convergence, or an infinite radius of convergence, so converge everywhere, right? Okay, and this seems like, you know, this thing seems like what? But you'll see, this is just referring to the fact that you can expand functions, most functions, in terms of a series, right? Which you probably already know. So we can take a look at that next. All right, so let's look at this analytic on a point idea, just meaning that, you know, as you know, and we can see over here, you know, there are expansions. They're called Maclaurin series or Taylor series if you're expanded around a particular point. And they are representations of the functions as infinite series, right? And sometimes they have these nice, well, most of the time, they have these nice closed forms as well, right? Like e to the x is sum over n equals 0 to infinity, 1 over n factorial x to the n, etc., right? And they have these intervals of convergence, okay? Most of them are minus infinity to infinity, but, you know, you'll have things like the log of 1 plus x, you know, it's not going to have minus infinity to infinity as its radius of convergence, which should make sense to you given the log function. All right, so you have like Cauchy and Sanch and the inverse tangent, etc. But you can always get a Taylor series of something by actually, or Taylor or Maclaurin series by, and I'm not going to write down what those are, but like, well, I guess I will write for the Maclaurin. So let's look at the Maclaurin series. Just how would you get one? Well, you can take your function and you take the nth derivative, right, in the series, and you evaluate it at 0, divide by n factorial, and multiply by x to the n, right? So for instance, the first one would be the 0th derivative, which is just the function itself, evaluated at 0. And then the next one would be f prime, evaluated at 0 over 1 factorial times x, right? And then the next one would be the second derivative, evaluated at 0. 2 derivative. 0 over 2 times x squared plus dot, 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 right? This is the Maclaurin series, the definition of how you would get it. But a lot of times you can just go look them up, right? Okay. Now, if you need to change some of these, right? So for instance, let's say you wanted to change, get a series for e to the x squared. Well, all you have to do is take everywhere you see an x, put an x squared. So this would be x squared, this would be x to the fourth, etc., right? And x to the sixth, and blah, 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 right? So it's pretty simple. Things like changing the, changing if you wanted to have an expansion for log ln of x instead of ln of 1 plus x, you can replace x everywhere, right, with x minus 1. So if you put x minus 1 here, then you just get ln of x, and over here you'd have x minus 1 squared, x minus 1 cubed. Okay, so you can manipulate these to get what you need. Okay. Now, there's a couple of operations on series that you really need to understand how to do when you're going to do series solutions for things. And one is multiplication of power series. So you take two power series and you multiply them together. How do you do that? And then the other one, which is a little more complicated, which you wouldn't think it is, but it is the addition of power series. So we'll look at the multiplication first. All right, so let's look at an example of multiplication of two series. So, oops, sorry. So we want to find the series representation of e to the x times sine of x. Okay, so let's multiply it out. So you already have the series here for these two. So let's see, we have e to the x is 1 plus x squared over 2 plus x cubed over 6 plus dot dot dot. And then the sine is this guy, right? So it's x minus x cubed over 3 factorial. And then plus x to the 5th over 120 plus, or no, minus, sorry, minus x to the 7 over 5040, all right, plus dot dot dot. We don't need this many terms. But that is that. And now we're just going to multiply through and collect terms. Now we don't have to do that forever, but we can do it until we see something, right? If we see a pattern, we may not see a pattern, but at least you can have the first few terms. All right, so we're going to look for anything that's a constant term. Well, there's a 1 here, but it's going to be multiplying powers of x, so there's no constant term. What about the first power of x, right? X to the 1. Well, I'm going to have 1 from this times this, and that is it, right? Because this times any of the other ones is not going to give me x to the 1. So I have x to the 1. Now I'm going to collect all terms that are proportional to x squared. So what do I have? I have 1. Well, but it's not going to give me an x squared over here, right? If I multiply x times x, I'll get an x squared, so that's a 1. And that's kind of it. What about x cubed? Okay, so we have 1 times this. We have minus 1/6. And then we have x squared times x. So we have plus a half. Okay, let's see. What about x to the 4th? Plus x to the 4th. Let's see. What do we get for x to the 4th? Well, this times this gives me x to the 4th, so that's a minus 1/6. And then x squared times, no, x cubed times x, so that gives me a plus 6, plus 1/6. So that's going to cancel out. And that's it. And then there's other terms, right? So I'm just going to stop there. So if we simplify this out, we get x plus x squared plus x cubed over 3. So I put that together. Minus x to the 5th, which I didn't write down, but you can prove to yourself that you get x to the 5th over 30 plus dot dot dot. Okay, you might do a few more terms just to see what you get. And that's what you do to multiply. It's pretty simple. You're just collecting terms of the same power. Okay, now adding series is a little more complicated, and it's a little more complicated because you need to have the same index, right? So the index here, so you need to have the same start of the index when you're done. Okay, well, let's see how that works. I'm going to get rid of all this. So get rid of this. Okay, new layer. All right, so let's look at addition of series. So let's look at the series sum of n. So the sum from n equal 2 to infinity. And we're going to add the two series together. So we're going to have this one, n minus 1, and c to the cn, and then x to the n minus 2. We want to add that, well, we want to subtract this next series from that, n equals 0 to infinity, cn, x to the n plus 1. Now notice here, this series starts at n equal 2, and so my first power will be x to the 0. This starts at n equals 0, so my first power will be x to the 1. And I can't really do anything with this until I fix these indices so that they're the same. Well, how do I do that? Well, for one thing, since this starts at x to the 0, and this starts at x to the 1, I better just take one term out, and I can totally do that. So I'm going to take one term out, the first term when n equal 2. And now n equal 2, I'm going to have 2 here. I'm going to have 2 minus 1, that's 1. So I'm going to get 2c2, and then x to the 0, which is 1. So I'm just taking it out. And then what's left is I'm going to have the sum from n equal 3 to infinity of n minus 1, c and x to the n minus 2. And then, of course, minus the second one. Okay, cn, x to the n plus 1. Now notice that now both of them start at x to the 1, because this starts at n equal 3, right? X to the 1, x to the 1, because that starts at 0. So let's just move these indices around. So how can we do that? Well, first we're going to look at this, right? And we're going to make a new index, k equals n minus 2, okay? And that tells me that n is equal to k plus 2. And I can write this first series, so let's just look at this guy. So I can write this first series, sum over k, right? So notice that when n equals 3, right, k equals 1. All right, so we're going to say, let's just leave the sum index off of that for a second and just look at, so n is k plus 2, right? So we're going to have k plus 2. And that's what this n is here. And then k plus 2 minus 1 is k plus 1. Oh, sorry, yeah, k plus 1. Right, that's going to be this thing. And then we're just going to have ck, because it doesn't matter what that thing is. Well, we should put it in terms of k plus 2 too. Okay. And then here we have x to the k. Now notice that to get n equal 3, right, I need k equal 1. So this is going to start at k equal 1 to infinity. And now we'll do the next one. Over here, we'll make a different choice. We'll say, okay, let's get k equal n plus 1, and that means n equal k minus 1. Okay, and to get n equals 0, right, it's k equal 1 again. So that's good. So let's just rewrite that one, and I'll put that over here. Sum k equal 1 to infinity, k equal 1 to infinity of c k minus 1 x to the k. So now they both start at the same place, and they both start with the same power, or they're proportional to the same power here. And now we can write them as a single sum. So we have our sum is equal to the sum k equal 1 to infinity. Oh, I forgot my term, the term that I took out. Let's do that. Okay, don't forget that term. So we have 2c2, and then we have plus the sum from k equal 1 to infinity, and then we have k plus 2, k plus 1, ck plus 2, minus ck minus 1, and then all of that is x times x to the k. Okay, so that really makes a big difference And you've now written your sum all as one thing, right, with one sum. So that's what you want to do when you're adding series. And you're going to see, maybe this seemed like complete craziness to you and Greek to you, but try to go back over it and look at some examples in your book and look at some problems in your book and make sure you know how to do this, because it's really crucial for the actual series solutions, which we're going to start studying in 6.2. But before we go to 6.2, I'm going to give you an example of a series solution. Okay, so let's kill that, get a new layer. All right, so we're going to make a power series solution. So we're going to have a power series solution, Cn x to the n, for the equation y prime plus y equals 0. Okay, so now we have to take a derivative of this. Oh, how do we do that? Well, it's just like taking a derivative of any other polynomial, right? So y prime, don't be afraid, you can go on to the sum, is sum n equals 0 to infinity of Cn times n times x to the n minus 1, right? Okay, now here, when n equals 0, this is just going to be 0, so I might as well start at n equal 1. So I'll write that as sum n equal 1 to infinity Cn n x to the n minus 1. Okay, fine. And so now when I put everything into the equation up here, so I'm going to use my derivative first. So I have sum n equal 1 to infinity. We have Cn n x to the n minus 1. And then I have plus y, right? Plus the sum n equals 0 to infinity Cn x to the n, right? And that has to equal 0. Now, notice here that I have different powers on the x, so I haven't really added these together the way I need to. So if I look here, this, if when n's 1, this is going to be 0. When n's 0, this is going to be 0. So they're actually starting with the right, the same power. That's awesome. So I'm going to change this. I'm going to let k, right? I'm going to change this guy. So I'm going to let k equal n minus 1. And so n is equal to k plus 1. And so my series becomes, and then notice that n equal 1 when k is 0, right? Okay. So I'm going to say sum k equals 0 to infinity, and then I'm going to have c k plus 1, then I'm going to have k plus 1, and then x to the k, right? Plus the sum from, and I'm free to just change the index to k here, because why not? I haven't changed anything on this, right? I'm just calling it a different thing. Instead of calling it n, I'm calling it k. ck x to the k. Okay, and now I can add them together correctly. So I have the sum k equals 0 to infinity of ck plus 1, k plus 1, then plus ck x to the k. Okay, cool. Now this whole thing is 0, right? Because that's what the equation says. It's 0 here. And now we can use that identity property, which is really another statement of the fact that when you make a linear combination of functions that are linearly independent, all those coefficients better vanish, right? If you've made that linear combination and if that linear combination adds to 0, then all the coefficients must themselves be 0. So that tells me that ck plus 1 times k plus 1 plus ck must be 0. Okay? And so that tells me something, because now I can solve for ck plus 1 in terms of ck. And in fact, I can do that. So ck plus 1 is equal to minus ck over k plus 1. So if I have C1, I can get C2. If I have C2, I can get C3, etc., right? Okay, that's cool. Remember that k starts at 0. 1, 2, 3. Okay, well, let's see if we can simplify this further by writing out the terms of this. This is called a recursion relation. Okay, and we're going to start with k equals 0. So k equals 0, that gives me C1 is equal to minus, right, C0. Now C0 is an arbitrary constant so far, so I'm just going to leave it that way. And what about C2? Well, C2 is minus 1/2 C1, which is minus 1/2 minus C0 from this, right? And so it's equal to 1/2 C0. C3 is minus 1/3 C2, which of course is minus 1/3 1/2 C0. This is 1/3 1/2 C0, and that of course is minus 1/3 times 1/2, and then oh yeah, this is C1. C1, and this is minus, so I've got a minus sign here. Let me just figure that out. I know what I did wrong. Let me just fix it. Okay, so I need to, I'm writing this in terms of C0 ultimately. Okay, so I'm not thinking here. All right, so this is minus 1/3, and then we have this is 1/2 C0 here, C2, right? C2. So 1/2 C, this is a third, not, okay. C2, and so we get this is minus 1/3 times 2, and then C0. Okay, so just, I'm not going to calculate each one, but let me just write down what this is. This is 1/4 times 3 times 2 times C0. I hope you're seeing a pattern. And so if we write all this down, right, so let's write down the actual series, right? So the series is this sum from n equals 0 to infinity of Cn x sub n, or x to the n. So let's just write out a couple of terms of that. So when n equals 0, we have C0, x to the 0, plus the next term, which is C1x, but C1 is minus C0, so minus C0, right? And then plus C0x, then plus C2x squared, but C2 is 1/2 C0, so we get plus 1/2 C0x squared, and then the next term, right, is C3x cubed, but C3 is minus 1/3 times 2C0, so minus 1/3 times 2 C0x cubed plus ... Now I'm going to just write down what this is, and you can have to look and see if you believe me. Sorry. I'm going to write down what the series reduces to. Well, it reduces to C0, and then the sum k equals 0 to infinity of -1 to the k, right, over k factorial. Believe that? Look through the terms, make sure. X to the k. Okay, and if we look through the actual series that we have, and let's see if I still have that somewhere here for you to look at. Yep, I do, although it's kind of messed up with stuff here. Anyway, but if we look, we can see that this is, if you put a negative in here, if you put a negative sign inside here, you get negative x to the k, right? And that would be e to the minus x here. So this is really C0 e to the minus x, which we know is the solution to this, right? So if you go through and substitute e to the mx in here, you'll get that the solution is e to the minus x, right? So we just verified that that's what it is. Okay, obviously you didn't need series solution to solve that equation, but this is the spirit of what we're going to be doing in section 2 and the rest of chapter 6. Okay.